4.4.7 Eutrophication and ecosystem services. Effects on fishing. In certain areas, an increase in nitrates and phosphates in water bodies can lead to an increase in productivity and an increase in the fish stock. Eutrophication can also affect the fish species that can survive in waters. Eutrophic waters tend to have dominant species, such as carp, which many people find to be less desirable than species such as salmon or trout. Carp may also disturb the sediments at the base of water bodies, which can lead to a decline in water clarity. The carp likes to mess around in the bottom sediments. In North America, some eutrophic water bodies produce large populations of stunted panfish. These populations grow in size as predators are unable to see them due to increased turbidity from planktonic algae and suspended sediments. The increase in algae in the upper part of the water not only stops light from reaching down to the water's depth, but also causes oxygen depletion, thereby affecting the quality and quantity of fish that can survive. Oceanic waters are generally nutrient poor, and fisheries are limited by the primary production that occurs there. However, there are some cases where marine water nutrients washed into coastal waters can lead to algal blooms or red tide organisms, such as dinoflagellates. Effects on recreation. The growth of large populations of macrophytes can reduce access to waterways, which reduces the potential of water bodies for fishing, sailing, paddleboarding, and swimming. The presence and smell of scum may make some water bodies unpleasant to view and smell. Right, so if you have too many macrophytes, too many water plants clogging up stuff, you can't really play there, and it can be stinky. Large numbers of species such as water hyacinths and Nile cabbage may cover large areas and move into open water, preventing light from reaching submerged plants. Okay, so some of these floating macrophytes or plants that create too much shade for the plants that are underneath. The presence of large quantities of dead organic matter in water bodies results in low oxygen concentrations and emissions of methane and hydrogen sulfide. They write it as CH4 and H2S, but that is methane and hydrogen sulfide, making it unpleasant for recreational users. Okay, so methane and hydrogen sulfide are kind of smelly. Aesthetics. Aesthetics refers to the appreciation of beauty. Many natural environments are very beautiful, but many have been degraded. Eutrophication has a range of negative environmental impacts, including reducing the visual appeal of streams and lakes. I mean, yeah, if you go out to a lake and it's full of scum, like full of scummy green algae, it's not that, is that appealing to swim in? Does that look very nice? Making water unsafe for swimming, certain types of bacteria, etc. It's not nice to swim in. Altering the biodiversity, making the area less attractive for environmentalists. Making areas less attractive for walkers due to the smell, right? So it gets stinky. Change the biodiversity, then you can't really, if you're going out to bird watching or something, or looking for certain kinds of frogs, or wanting to see certain kinds of flowers or unique species, basically like the unique species of the area. If you have low biodiversity, it's not that interesting. Health concerns. One of the health concerns relating to eutrophication is increased rates of stomach cancer, which can be caused by nitrates in the digestive tract. Okay, so we talked about the safe levels of nitrates in drinking water, because it can cause stomach cancer. But critics argue that the case against nitrates is not clear, as stomach cancer could also be caused by a variety of other factors. However, in some parts of Nigeria where nitrate concentrations have exceeded 90 milligrams per cubic decimeter, the death rate from gastric cancer is abnormally high. Well, that seems like quite strong evidence, but could be other things. Another health concern is blue baby syndrome, methemoglobinemia. Well, that's a mouthful. Which is caused by insufficient oxygen in the mother's blood for the developing baby. Okay, so this is talking about pregnancy. Critics argue that the number of cases of blue baby syndrome is statistically small. However, according to the Department of Health in Minnesota, USA, when nitrates in well water, so well water is water found in wells, exceed 10 milligrams per liter, this can trigger methemoglobinemia in infants under 6 months of age. That's interesting. I wonder if there's nitrates in the water and they mix it with the formula, if that's going to cause this problem. Otherwise, they were talking about That's interesting. I wonder if this is just an issue with formula, or if this is somehow affects the breast milk as well. It doesn't say. That might be interesting to look up. If nitrates in the water is a issue for babies, just babies who are drinking formula that's made with the water. We have a powdered milk mixed with water from the local well or wherever, or if there's an issue with breastfeeding as well. Managing eutrophication. Water pollution management strategies. Eutrophication can be addressed at 3 different levels of management. These are reduction of human activities that produce pollutants, for example, using alternatives to current fertilizers and detergents, putting less in, right? Creating less of the problem. Reduction of the release of pollution into the environment, for example, treatment of wastewater to remove nitrates and phosphates. Okay. And removal of pollutants from the environment and restoring ecosystems. For example, removal of mud from eutrophic lakes and reintroduction of plant and fish species. Okay, so reducing the amount of pollution we put in there in terms of fertilizers, detergents, and wastewater, and then also trying to restore the degraded ecosystems. Altering human activities. Public campaigns in Australia have encouraged people to reduce eutrophication by using 0 or low phosphate detergents. So you can check on the bottle or box of detergent that you have and see if it's phosphate free or low phosphates. Washing only full loads in washing machines. Washing vehicles on porous surfaces away from drains or gutters. Reducing the use of fertilizers on lawns and gardens, composting garden and food waste, and collecting and burying pet feces. Okay, so not letting the dog and cat poop just be everywhere. And then we've got this washing of the vehicle, so porous surfaces, that means like on the grass, so that the detergent water that you're using to wash the vehicle goes down into that the soil instead of washing into the drains and gutters, which then takes it directly to the streams and ponds. Okay, so figure 4.80, pollution management targeted at 3 different levels. Okay, so here you can see the process of pollution, the human activity, release of pollutant into the environment, impact of pollutant on ecosystems, and the 3 different levels of pollution management, addressing those processes. Up to 45% of total phosphate loading to freshwater in the UK comes from sewage works, so waste treatment plants. This input can be reduced by 90% or more by carrying out phosphate stripping. The effluent is run into a tank enclosed with a precipitant, which combines with phosphate in solution to create a solid. The solid then settles out and can be removed. So you've got the sewage water, and after the solids have been removed, you still have like the phosphates in the water, and so you can add a chemical that will bind these phosphates and create like a solid substance that then falls out. Possible measures to reduce nitrate loss. Measures used on the mid-latitude northern hemisphere include the following. Avoiding the use of nitrogen fertilizers during the wet season when soils are wet and when the fertilizer is therefore most likely to be washed through the soil. Giving preference to autumn-sown crops as their roots conserve nitrogen in the soil and use up the nitrogen left from the previous year. Okay, so why are we concerned about nitrate loss? Okay, so we don't want to have to add fertilizers. Well, like nitrate, it goes with the water. So when it rains or when you've got irrigation going on, though, the nitrates like to go into the water and then wash away. So that's the nitrate loss, because that nitrate loss, actually, the nitrates, where do they go? They go into the streams and then into the lakes or the oceans or wherever, and then they cause this eutrophication stuff. So we want the nitrate to stay in the soil. And so these are ways to help keep the nitrate where it is. So sowing autumn, and this is sowing as in planting, not sowing as in with a needle and thread. Okay, sowing autumn crops as early as possible and maintaining crop cover through autumn and winter to conserve nitrogen. So not letting the fields just be bare. Avoiding the application of nitrogen-based fertilizers when the field is by a stream or lake. That makes sense. Don't add on nitrogen fertilizers when there's a high chance that they're going to wash away into a local stream or lake. Avoiding the application of nitrogen-based fertilizers just before heavy rain is forecast, assuming that the forecasts are accurate. And using less nitrogen if the previous year was dry, because less will have been, although this is difficult to assess precisely. There's a word missing here. Using less nitrogen if the previous year was dry, because less will have been. I think this should be less will have been washed away, or less will have been lost. So don't just automatically apply, like if you're adding, using less nitrogen in the previous, using less nitrogen if the previous, yeah, instead of just adding nitrogen fertilizer based on a certain amount, like, oh, I always add this much every year. If it was dry the previous year, use less because less was washed away the previous year. Regulating and reducing the nutrient source. Prevention of eutrophication at source has the following advantages compared with treating its effects or reversing the process. Technical feasibility. In some situations, prevention at the source may be achieved by diverting, like moving, a polluted watercourse away from the sensitive ecosystem. The removal of nutrients from a system by techniques such as mud pumping is more of a technical challenge. Cost. Nutrient stripping at source using a precipitant, that's what I was talking about the sewage treatment plant, is relatively cheap and simple to implement. Biomass stripping of affected water is labor intensive and therefore expensive. So biomass stripping, that means like going in and physically scooping up all the algae and getting rid of it that way. That's a bit intense. Products. Restored wetlands may be managed to provide economic products such as fuel, compost, or thatching material more easily than trying to use the biomass stripped from a less managed system. Okay, so going in and harvesting some of the reeds and stuff. That's interesting. Cleanup strategies. Once nutrients are in an ecosystem, it is much harder and more expensive to remove them than it would have been to tackle the eutrophication at source. Right? So stop it from happening to begin with. The main cleanup methods available are precipitation, which is treatment with a solution of aluminum or ferrous salt to precipitate phosphates. Okay, so you add a chemical, binds to the phosphates, it makes them fall out of the water. Right? Or precipitate, come out of the water, come out of being dissolved. Removal of nutrient-enriched sediments by, for example, mud pumping. Okay, so if you've got a lot of these nutrients built up in the sediment, then they get released into the water during the summer months, and so we don't want that. So they just get rid of the mud. That seems. Removal of biomass, for example, the harvesting of common reed and using it for thatching or fuel. Temporary removal of fish can allow primary consumer species to recover and control algal growth. Once water quality has improved, fish can be reintroduced. Mechanical removal of plants from aquatic systems is a common method for mitigating the effects of eutrophication. Right, so going in and chopping down the plants that are there. Efforts may be focused on removal of unwanted aquatic plants such as water hyacinth that tend to colonize eutrophic water. Each 1,000 kilograms of wet biomass harvested removes 3 kilograms of nitrogen and 0.2 kilograms of phosphorus from the system. Alternatively, plants may be introduced deliberately to mop up excess nutrients. Okay, so it's really going to be system dependent. You're going to have to look at, and this is what a lot of government ecologists or environmental consultants do. They look at a specific lake that has a eutrophication problem, and they design a tailored solution to that depending on what species are there and what is going on. Because eutrophication is this kind of umbrella term. So when it comes to what is actually happening in a specific lake, they've got to look through these different factors and say, okay, what is doing what here? And how can we best fix this issue given the resources that are available? In some circumstances, it may be possible to divert sewage effluent away from a water body. Okay, so not putting the sewage in the river, putting it somewhere else. This was achieved in Lake Washington near Seattle, USA in 1955. Cyanobacteria affected Lake Washington. The lake was receiving sewage effluent from about 70,000 people. The sewage system was redesigned to divert effluent away from the lake to the nearby sea inlet of Puget Sound. Okay, so they diverted the sewage from the lake to the sea instead. Well, fixed the eutrophication issue at the lake anyway. Not quite sure what happened to Puget Sound. 4.4.9 Pollutants in water. Pollutants in water include organic matter, dissolved substances, persistent chemicals that get biomagnified, plastics, and heat energy. All right, we're going to look at this little example, water pollution in the Ganges. The Ganges is the longest river in India and provides water for about 500 million people. It is said to be the most polluted river in the world and is heavily polluted with human waste as well as agricultural and industrial discharge. It flows through a number of industrial cities such as Varanasi and Patna, which have large numbers of factories, chemical plants, distilleries, that's where you make alcohol, textile mills, that's where you make cloth, tanneries, that's where you make leather, slaughterhouses, you slaughter animals, you kill animals, and some coal-based power stations. The burning of coal produces fly ash, which contains heavy metals such as lead and copper. All right, now back to the main text. Water pollution includes sewage, dissolved substances, persistent chemicals, plastics, and heat energy. Tributyltin TBT, tributyltin, is an example of a dissolved substance in water. TBT was for many decades used as a biocide to prevent the attachment of organisms to ship hulls. Okay, so they would paint this stuff onto the hull of a ship to prevent like barnacles and stuff from growing on the ship. The TBT slowly leaks into the marine environment, where it can have a major impact on non-target species. Okay, so non-target species, a target species is what the biocide is trying to kill or trying to repulse, make it go away and not be there, right? But non-target species means it's affecting other stuff. Through bioaccumulation and biomagnification, TBT can make its way up the food chain. TBT can lead to immunosuppression in dolphins and sea otters and can cause hearing loss in toothed whales. Humans exposed to TBT may experience fatigue, respiratory problems, and headaches. Long-term exposure may impact the kidneys and the liver. PCBs, polychlorinated biphenyls, are human-made persistent chemicals, such as pyranol, that are used in air conditioning units. They were produced in large quantities for use in transformers, paints, sealants, and machinery. Plastics may also contain PCBs. PCBs can accumulate in your fatty tissues and through bioaccumulation and biomagnification. They can be harmful to top predators such as seals, tuna, polar bears, and humans. In humans, they have been linked with increased risk of cancer, suppression of the immune system, failure of the reproductive system, and interference with hormone systems. That's not good. Heat energy is also a form of pollution in water. Heat energy may come from industrial waste or from cooling towers in power stations. It might also occur due to vegetation removal along the sides of lakes and riverbanks. So taking down the trees that shade the water. This may allow more solar energy to reach the water. Changes in water temperature can have a significant impact on water chemistry and the ecosystem. So some places they use water to cool down the machines, and then so they pump in cold water, use it to cool down the machines, which heats the water out, and then they dump the hot water out into the ocean or into the lake. And like it's clean-ish, like it's not that they haven't dirtied the water, they've just heated it. But now you have hot water in the part of the lake that they're dumping it into. And the impacts of that, of changing the temperature like that, can be reduction in the amount of dissolved oxygen, increase in the amount of toxins present, loss of biodiversity, changes in ecology, migration of species, an increased metabolic rate within organisms. There's all kinds of different effects that can happen there due to changing the water temperature. 4.4.10, harmful algal blooms. Harmful algal blooms contain a variety of organisms, including cyanobacteria, protists, algae, and dinoflagellates. A small number of these organisms produce potentially fatal toxins. In freshwater, cyanotoxins are the most common toxins. Within the harmful algal blooms, HABs, that occur along coastlines, dinoflagellates produce different toxins, including neurotoxins. Other algae may be non-toxic, but can use up all the oxygen in a body of water. Well, that's, indirectly, okay? It's due to the decomposition stuff. They are not themselves using up the oxygen. Protists are a set of organisms that are not classed as animal plant bacteria or fungi protists. Examples of protists include amoebas, brown algae, and red algae. Okay, so those aren't phytoplankton. Those are something else. Those are protists. We have an example about harmful algal blooms in the USA. So it's about how it's just some economic examples here of financial damage due to algal blooms and because of how they affect tourism for the most part and recreation. Freshwater. In freshwater, cyanobacteria produce cyanotoxins. People can come in contact with these through recreational water activities, drinking contaminated water, breathing in contaminated air droplets, and eating contaminated shellfish and fish. Symptoms include irritation of the skin, eyes, throat, lungs, and or nose. So cyanotoxins produced by cyanobacteria are not good. Not for us anyway. Marine waters. Along coastlines, dinoflagellates are a major component of HABs. Many dinoflagellates produce neurotoxins, many of which are extremely dangerous. Consumption of seafood contaminated with algal toxins could lead to paralytic shellfish poisoning, neurotoxic shellfish poisoning, amnesic shellfish poisoning, and diarrheal shellfish poisoning. Okay, so basically, when you're having shellfish poisoning, it's because there are toxic algal substances on the shellfish. In many cases, toxic dinoflagellates are present in low concentrations with no environmental or human impact. So they're allowed to be there. Like they don't, when there's not that many of them, they don't cause a problem. However, when present in high density and ingested by shellfish, zooplankton, and herbivorous fish, toxins bioaccumulate and biomagnify up the food chain. So when they're talking about the shellfish poisoning, the contamination, it's because the shellfish have eaten it. Okay. And they have accumulated these toxins in their flesh. 4.4.11, anoxic and hypoxic water. Hypoxia, low oxygen, and anoxia, lack of oxygen. So anoxia is no oxygen, hypoxia is low. In water result from several causes and can create aquatic dead zones. The frequency of anoxic, hypoxic waters is likely to increase due to the combined effects of global warming, freshwater stratification, sewage disposal, and eutrophication. Hypoxia and anoxia are very common in stagnant water. That's water that is not moving. Many conditions can lead to hypoxic waters. Warm water, which could be due to factory discharges. That's what we're talking about, cooling down the factory equipment. Shallow water or summer heatings hold less oxygen than cold water. Acute incidents may be caused by excessive use of nutrients on farms, discharge from sewage plants, and from bird or animal waste. The overloading of nutrients results in algal bloom, which deprives submerged plants of sunlight. When the algal bloom dies and sinks to the bottom of the water body, it decomposes, taking oxygen out of the water. So that's why algal blooms cause loss of oxygen. It's because of when they decompose. Okay. Sheltered bays with low wind speeds and gentle currents may allow water to stratify, by temperature, right? Forming a layer of low oxygen water near the surface. Anoxic and hypoxic water have, for example, limited dissolved oxygen, but large amounts of phosphorus and nitrogen, and experience phytoplanktonic blooms. Okay. So figure 4.82 is the characteristics of anoxic and hypoxic water. And there is an example, the development of hypoxia in Narragansett Bay in Rhode Island, in the USA. Narragansett Bay is a temperate estuary that experiences low oxygen, which is hypoxic, events most summers. These events generally persist for a few days to a week, several times each summer. Prior to the late 1990s, the bay was considered to have low vulnerability to hypoxia, despite high levels of nitrogen. However, as nutrient loading continued, hypoxia increased in frequency, as did the length of each event. In 2003, low oxygen levels in the water led to the death of some 1 million fish. So you can have these events that cause massive fish kills. This was followed in 2004 by increased mortality among clams. As a result, Rhode Island passed a bill in 2004 that set the nitrogen limits for the area's largest wastewater treatment facilities. By 2006, the summer levels of nutrients were reduced by over 1/3 compared to the levels between 1995 and 1996. They continued to reduce and have since been reduced to half compared to the levels from 1995 to 1996. Okay, so they created some laws on the waste treatment facility saying how many nitrates they could or nutrients they could it was nitrogen limits, how much they could release. So they had to use technology and methods to take that out of the water that they were releasing, out of the effluent that they were releasing into the water. 4.4.12, sewage treatment. Sewage is treated biologically and chemically to allow the safe release of effluent by primary, secondary, and tertiary water treatment stages. There are major variations in access to sewage treatment around the world. So figure 4.83 is what sewage treatment in a septic tank looks like. Sewage treatment aims to remove contaminants from sewage to produce a clean, safe effluent that can be discharged into the surrounding environment or used again for another purpose. Sewage treatment involves at least two stages, primary and secondary treatment. And advanced treatment has a tertiary stage, tertiary means third, with disinfection and even a fourth stage to remove micropollutants. Types of sewage treatment can be divided into high technology, expensive, intensive treatments, and low cost, low technology, extensive, or natural treatments. Primary stage. Primary sewage treatment refers to the removal of some of the suspended solids and organic matter from the sewage. The sewage is allowed to pass slowly through a primary sedimentation tank, which is a basin, in which heavy solids sink to the bottom. Lighter solids, oil and grease, rise to the surface and can be skimmed off. About 50 to 70% of suspended solids are removed in the primary sedimentation tanks. Secondary stage. Secondary sewage treatment uses biological processes to digest and remove organic material. Microorganisms that feed on organic matter grow and multiply, reducing even more of the organic matter. This can be done aerobically or anaerobically, so with oxygen or without oxygen. The tertiary stage. Tertiary sewage treatment or advanced treatment provides a final stage to improve effluent quality before it is discharged. More than one tertiary treatment may be used. If disinfection is used, this becomes the final stage. This is also known as effluent polishing and can also involve biological nutrient removal. In some situations, treated sewage, that biological nutrient, that's like pulling the phosphorus out of the water, right? In some situations, treated sewage may be stored in large-scale ponds or lagoons. Macrophytes, such as reeds, may help to filter out some of the treated sewage. Disinfection may also be used in order to kill any microorganisms that could be carrying diseases. Chlorination is the most widely used form of disinfection owing to its effectiveness and low cost, although iodine and other chemicals can also be used. The use of ultraviolet light as a form of disinfection is becoming widespread in many countries owing to concerns about the side effects of chlorine. So there's lots of pathogens and diseases that can be carried in water. So they want to disinfect it. Treatment differences in high-income countries and low-income countries. In 2021, it was estimated that 52% of sewage is treated globally. However, for many parts of the world, there is little data available. In high-income countries, 74% of sewage was treated, but in low-income countries, only just over 4% of sewage was treated. Okay, so that means 96% of the sewage in low-income countries is just going straight into the lakes, streams, and oceans, or into the ground. In urban areas of high-income countries, sewers take waste products to a sewage treatment plant, whereas in low-income countries, the bulk of wastewater is discharged directly into rivers and the ocean without any treatment. High-income countries treat about 70% of the wastewater they produce, whereas only about 8% of wastewater produced in low-income countries is treated. So here you can see global variations in domestic water that is safely treated. 4.4.13, water pollution and indicator species. An indicator species is one whose presence, absence, or abundance, so whether it's there or not, and how much of it is there, can be used as an indicator of pollution, like a signal. It does not have to be water pollution. Some species can be used to indicate air pollution, soil nutrient levels, and abiotic water characteristics. For example, lichen can indicate, a specific lichen species can indicate very low levels of sulfur dioxide in the air. Nettles can indicate high phosphate levels in soil. And red algae indicates saline rock pools as opposed to brackish ones. So we have figure 4.85 of indicator species. Certain species are tolerant of organic pollution and the low oxygen levels associated with it. They are found in high population densities where an organic pollution incident occurs. Right? Because they survive there, these ones that are tolerant to certain pollutions, they survive while everything else dies or disappears or goes somewhere else. So if you find a whole bunch of a specific species that's known to tolerate pollution, and you don't find much of anything else, probably means that pollution is there. Other species cannot tolerate low oxygen levels, and if organic pollution enters the river where they live, they move away or die. These groups can be used as indicators of organic pollution and are known as indicator species. Organic pollutants in water can be more dangerous in summer. This is because the solubility of oxygen decreases as water temperature increases. Warmer water, less oxygen. So on warm days, there's less available oxygen in the water. Aquatic invertebrates and fish can do little to regulate their body temperature. Therefore, as the water temperature increases, so does their internal temperature, along with their rate of respiration. This means they need more oxygen, but the amount of oxygen dissolved in the water is going down. If warm organic pollutants are released into rivers, the effect can be devastating. Figure 4.86 illustrates how tubifex worms and stonefly nymphs can be used as indicator species. The tubifex worms feed on and tunnel into effluent. Their populations increase rapidly immediately downstream of any effluent entry. Okay, so they like the sewage. A high population of these organisms in any river could indicate that organic pollution has recently occurred. In contrast, the population of stonefly nymphs crashes as soon as effluent enters their habitat. So stonefly nymphs don't like the sewage. They need clean water, and at the point of effluent entry, either die or move away. Thus, the absence of stonefly nymphs in a particular river might indicate organic pollution has occurred, and large populations might indicate clean, unpolluted water. It is often faster and cheaper to measure the populations of indicator species organisms such as tubifex or stonefly nymphs than it is to measure the concentration of specific pollutants. This is one of the advantages of using indicator species. Table 4.15 shows how the types of fauna, organisms like animals, present in a waterway relate to the levels of BOD, which was the biochemical oxygen demand. So you can see in this table, they've classed water into 5 different groups, 5 different classes, according to how high of a biochemical oxygen demand there is. And then like what you can, based on that, what it is safe to use the water for. Okay. So and then this is about indicator species. So if you see salmon and trout in the water, grayling, stonefly, and mayfly nymphs, and caddis larvae, And Gammarus are kind of, they kind of look like roly-polies, but they live in the water. Okay, then your water is probably in pretty good shape. Generally, water bodies that are in healthy biological condition are able to support a wide variety and high number of macroinvertebrate taxa, including many that are intolerant of pollution, such as freshwater shrimps, stonefly, caddisfly, and mayfly larvae. Samples yielding only pollution-tolerant species, such as bloodworms and sludge worms, or that have very little diversity or abundance, may indicate a less healthy body of water. Otters and wetland quality. Otters live in freshwater, brackish water, and seawater. These carnivores feed mainly on fish, amphibians, and crustaceans, and to a lesser extent on waterfowls, mammals, and reptiles. However, otter numbers have fallen in many parts of Western and Central Europe. They face several threats, including habitat destruction, wetland drainage. That's what it sounds like, wetland, when you drain off the water from wetlands to use that land for something else. River regulation and increasingly water pollution. Contamination of fish prey with pesticides and PCBs is a major cause of the decline. Due to their sensitivity to environmental stresses, otters are considered to be a good biological indicator for the quality of a wetland habitat. Thus, the disappearance of otters in many parts of Europe reflects the environmental damage to wetlands. 4.4.14 Biotic Index. Trent Biotic Index. The Trent Biotic Index is based on the disappearance of indicator species as the level of organic pollution increases in a river. This occurs because the species are unable to tolerate changes in their environment, such as decreases in oxygen levels or light levels. Those species that are best able to tolerate the existing conditions become abundant. That means they proliferate. There are lots of them, which can lead to a change in diversity. In extreme environments, such as highly polluted rivers, diversity is low. Very few different types of species can survive there. However, the number of individuals from pollution-tolerant species may be high. So you might have a lot of bloodworms and sludge worms because they can survive. Diversity decreases as pollution increases. That's key. Diversity decreases as pollution increases. 4.4.15 Water Quality Index. The Water Quality Index, WQI, was developed in the 1960s and has become a popular tool among water scientists. There are four main stages in the WQI model. The first is the selection of water quality parameters. The second is the generation of sub-indices for each parameter, so breaking it down into smaller parts. The third is the allocation of weighting values, how much which parameter should be considered. And four, addition of all sub-values to find the overall WQI. So water is crucial for life, but it is widely known that water quality has been in decline in many areas for a long time. Some of this could be natural, due to tropical cyclones or El Nino events, but much of it is anthropogenic, due to human activities such as intensive farming, mining, and waste disposal. A water quality index is a single weighted average, combining the results of several water quality parameters for a given water body. So figure 4.87 shows the most frequently used water quality parameters. Poor water quality is a problem wherever it occurs, in high-income countries and low-income countries alike. It is likely to increase due to population growth, rising living standards, and global climate change. There are many local variations in the parameters used in the WQI, considering local conditions. There are at least 35 variations of the WQI. Most WQIs have been designed to assess river quality, but some have been used for lakes, reservoirs, estuaries, and groundwater. The number of parameters used in WQIs varies from 4 to 26. The most common parameters used include temperature, turbidity, dissolved oxygen, suspended solids, total dissolved solids, fecal coliforms, BOD and nitrogen. However, a number of WQI models do not include suspended solids, microbiological contamination, and toxic compounds due to the high cost and lack of modern laboratory facilities. 4.4.16 Drinking Water Standards. There are no universally accepted national standards for drinking water. I might find that surprising. Drinking water guidelines have been suggested by the WHO, the World Health Organization, and local governments can set their own standards. However, where drinking water standards do occur, they are generally guidelines and targets for the levels of fluoride, lead, nitrates, and selenium. Very few have any legal enforcement apart from the European Drinking Water Directive and the Safe Drinking Water Act in the USA. Okay, so in this table 4.17, you can see variations in drinking water standards, which means like what's allowed and what isn't allowed to be in the water. And then there's an example here, access to drinking water in Monterrey, Mexico. And that's a good example of the conflict between international companies and local residents over access to water. So that's an interesting example to read about conflict. 4.4.17, reducing water pollution. There are several actions that individuals and groups of citizens can take to reduce water pollution. These include changes in consumption and waste disposal, protesting, data collection, lobbying politicians, and forming legal teams. There are many ways that people can reduce water consumption and pollution. These include not pouring fat from cooking or any type of oil or grease down the sink. Okay, so that instead you pour it into a jar or container, a little box, and let it solidify, and then you throw it out in the trash. So don't throw oil and grease down the drain. Not pouring household chemicals or cleaning agents down the sink or the toilet. Not flushing any pills or medication down the toilet. The toilet is not a magical portal to an alternative universe that just whisks away or whatever. No, like if you are putting something in the toilet, it is very likely going into the rivers and lakes. And we just talked about what water sewage treatment plants do, and well, they don't have magical filters for filtering out your medication. The processes of water treatment plants can degrade some kinds of medication, but not remove it completely. Installing a water-efficient toilet, using less water. Only running the dishwasher or washing machine with a full load. It's not just running it every day with 2 shirts. Using the minimum amount of detergent when washing clothes. Remember the detergents have phosphates? Or phosphates? Yeah. Minimizing the use of herbicides, pesticides, and or fertilizers, because when it rains, those things get washed away into the streams. Turning off taps when running water is not necessary. And that is the end of chapter 4. Don't forget to look at the end of chapter questions here and work through them so that you remember what you've read. It's a good idea.